Hello and welcome. This is Tracy, and we are going to talk about estimating the population proportion with some examples and some calculator steps. In this section, we are going to describe the requirements for finding a point estimate and confidence interval for a population proportion. We are going to construct and interpret a confidence interval for a population proportion, find and interpret the margin of error, calculate the required sample size to estimate a population proportion with a desired level of confidence and a desired margin of error. And remember, a proportion is just a number of successes divided by the number of subjects. For a population proportion, P is the symbol we use to represent a population proportion. We take X, the number of successes, divided by capital N, the number of subjects in the entire population. We usually can't get data on the entire population. We usually can't take a census. So instead we take a sample. And then we get P hat. This is the sample proportion with X, the number of successes in the sample, divided by little n, the number of subjects in the sample. We use that P hat as our point estimate to estimate the population proportion. Our sample proportion is our estimate for the population proportion. Now here we have our requirements for finding a point estimate, for finding that P hat, and for finding a confidence interval for a population proportion. First of all, we need a good study. If we don't have a good study, our results are at best meaningless and at worst misleading. They can give us bad results that lead to bad decisions. So we need a simple random sample for an observational study or randomized experiment. We need to make sure we eliminate all sources of bias. And in an experiment, we want a double-blind study with a reasonable control group, a control group that receives either a placebo or a conventional treatment as opposed to nothing at all. So we can take into account the placebo effect. Our underlying distribution must be binomial. We need a fixed number of trials or a fixed number of subjects. Each subject could be considered its own trial. Each trial or each subject can have two possible outcomes, either success with a probability P or failure with probability Q. And remember Q, the probability of failure, is just 1 minus the probability of success. And all of our trials or subjects need to be independent. We also need a large enough sample size. In order to find a confidence interval, or later on perform hypothesis testing, we are using the fact that a normal distribution can approximate our binomial distribution. But in order to have a normal approximation to our binomial distribution, we have to have successes and failures both be at least 10. At least 10 successes and at least 10 failures in order to find confidence intervals and to have a meaningful point estimate for our population proportion. We can't verify all of these requirements in our homework. In the real world, make sure you have a good study. Make sure that you have verified everything. But in our homework, well, we can verify that we have a fixed sample size. We'll be told that in a sample of 1,000 people or 200 subjects were chosen for this study or something along those lines. We can verify that we have our two outcomes, success and failure. Typically, the probability of success will be given or the number of successes in our sample, and we use that as our probability of success. And from that, we get the probability of failure, 1 minus the probability of success. And then we want to verify that we have at least 10 successes and failures. If we are given in our sample 700 people were successes, well, then use your sample size to calculate the number of failures. Make sure they are both at least 10. In the text and online homework, we usually have to assume that we have a good study. We're not told all the details. If you see phrases like random sample, stuff like that, that can really help you out and help you believe it's a good study, but a lot of times we can't be sure. We also are going to need to assume that our trials or subjects are independent. A lot of times that's not given to us either. So we just need to make some assumptions. Now, we're going to construct and interpret a confidence interval for a population proportion. And we're going to use an example that I pulled out of the online homework. This is the NASA G-forces example. So when you do the online homework, you'll see problems similar to this, as well as some other problems that are similar. So step one, NASA is conducting an experiment to find out the fraction of people who black out at G-forces greater than 6. And that word fraction, that tells you that we're looking for a proportion, in the same way that finding a percentage tells you that we're looking for a proportion. So we have a sample of 1,487 people drawn. Of these people, 669 passed out at G-forces greater than 6. Using this data, we want to estimate the proportion of people who pass out at more than 6 Gs. And it asks us to enter your answer as a fraction or a decimal number rounded to 3 decimal places. So we're going to want to be careful on how we do our rounding. So again, we know this is a proportion problem because we are asked to find out the fraction of people who black out at G-forces greater than 6. We want to verify the requirements that we can that tell us that we are able to use the techniques and have meaningful results. So this is a NASA study. We're going to hope that NASA, these guys are rocket scientists, they're smart enough to create a good statistical study. We have a fixed number of subjects, 1,487. Each subject has 2 possible outcomes. What we're trying to figure out is the fraction or proportion who pass out at 6 Gs. 6 Gs, or I'm sorry, at greater than 6 Gs. So that's our success. Now, granted, this is not what NASA wants. They want people who don't pass out. So a success, again, just means the outcome that we are looking at, the outcome that we're studying. It doesn't mean a good thing or a bad thing or what we want. It's what we are investigating. And then the failure is that the subject did not pass out at G-forces greater than 6. Do we have a large enough sample size? Well, our number of successes is 669. 669 people passed out at G-forces greater than 6. Yeah, that's at least 10. Plenty there. Is our number of failures also big enough? Well, we take our sample size of 1,487 and subtract off those 669 successes, leaving us with 818 failures, which is also at least 10. So we have a big enough sample size. We can do the stuff we're going to do and get meaningful results. So in order to find the population proportion estimate, the estimate for the population proportion, the point estimate for the population proportion of people who pass out at more than 6 Gs, all we do is we find our sample proportion. So we take the number of successes in our sample, that's 669, and we divide it by our sample size, that 1,487. We do that, and we get this big long decimal business, but we want to round to 3 decimal places. So 0.4498, that 4th decimal place of 8 tells us to round up. So 449 rounds up to 450, and put that 0 at the end. That shows you've rounded the full 3 decimal places. 0.450 is more accurate than 0.45 because 0.45, well, that could have been 0.450 or 0.451 and you rounded down, or 0.452 and you rounded down, or and so on. So put your 3rd decimal place on there. Now step 2, same scenario, but in this case, we want to construct the 98% confidence interval for the population proportion of people who black out at G-forces greater than 6, because we know that every sample we take is different. And so every time you're probably going to get a different sample proportion. So we want to figure out a range of values that we believe contains our true population proportion. And again, we're going to round to 3 decimal places. So we're going to do this in our TI. And our book goes through many steps and calculations, but it is very easy to do this on our calculator. We only need 3 pieces of information. We need X, the number of successes, we need N, the sample size, and we need the C level, the confidence level, which is the size of the confidence interval turned into a decimal. So in our situation, we have a sample of 1,487. That's N, our sample size. Of these people, 669 passed out. That is X, 669 successes. We want a 98% confidence interval, so our confidence level is 98%. Turn that into a decimal, 0.98. These 3 values, stick them in our calculator, out pops our confidence interval. And here I'm writing down the steps, and then in the next slide I give you a video link, a video for how to do this on your calculator. So on our TI, back to our favorite button, Stat, arrow over to Tests, and we want a 1 proportion Z interval. We are studying one group. We only have one sample, people, 1,487 people, so it's a 1. We are trying to estimate a population proportion, so that's where we get the 1 prop, P-R-O-P, for proportion. Because it's a proportion, we have a binomial distribution, but we are using a normal or a Z distribution to approximate the binomial distribution. That's where the Z comes from. And we are trying to find a confidence interval. That's where the INT comes from. So, stat tests 1 proportion Z interval, hit enter, and then it will prompt you. Put in your X, put in your N, put in your C level. Some of the calculators say calculate, some of them say paste, which whatever, highlight the calculate or the paste or enter, 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 and here's the video. Alrighty, let's go ahead and walk through the calculator steps in order to find the confidence interval that we've been talking about for our NASA G-forces experiment. We are finding a confidence interval. Anytime we want to find a confidence interval, we go to our favorite button in the stats class, the stat button. A confidence interval is a form of a test. So go ahead and arrow over to the tests. And even though confidence interval doesn't have the word test in it, as you can see, Z interval, T interval, well, we did those last time. Keep going down to the 1 proportion Z interval. We are looking at a single 1 group. We are finding an estimate for a population proportion, prop there. This is a proportion, so we have a binomial experiment, but we are using the normal or Z approximation, and it is a confidence interval, int. So go ahead and hit enter. And now we just enter the information. X is the number of successes, the number of subjects that actually did pass out of the sample of 1,487 subjects. Our confidence level is our confidence interval of 98% turned into a decimal. 98% is the same as 0.98. And then we just calculate it. And bam, out pops the confidence interval. This is what you get. So this is the result that you get. 0.41989, comma 0.47991. Ooh, and there's that p hat that we found earlier. Actually, you could have found your p hat this way, even before taking your number of successes divided by your sample size. But this is a good way to check to make sure that you're not doing things backwards. And it tells you your sample size. So here's our confidence interval. The left-hand number in the parentheses is the lower bound of our confidence interval. The right-hand number is the upper bound. Now we were asked to round this to 3 decimal places. So we're going to round this to 3 decimal places, and then we're going to find our margin of error. So this confidence interval in the calculator becomes 0.420. Our lower bound is 0.420. Remember, we round that 0.4198. The 8 rounds the 9 up, so 419 becomes 420. The upper bound, 0.4799. That 9 rounds the 479 to 480, and that's our upper bound. And we had a sample proportion of 0.450. So our margin of error is the difference between that sample proportion and the lower bound, or the difference between the upper bound and the sample proportion. Our margin of error is what we add and subtract to our sample proportion to get those upper and lower bounds. So 0.450 minus 0.420 gives us a 0.03. 0.480 minus 0.450 also gives us a 0.03. So our margin of error is 0.03, which is the same as 3%. Depends on how you're choosing to answer the problem or describe your data if you are doing this in a real-world situation. Now we're going to go ahead and interpret that confidence interval and margin of error. And that 98% confidence interval tells us that we are 98% confident that the true proportion of people who passes out at G-forces greater than 6 is between 0.420 and 0.480. Or we are 98% confident that between 42.0% and 48.0% of people passes out at G-forces greater than 6. Another way we could say the same thing, we estimate the proportion of people who passes out at G-forces greater than 6 to be 0.450 plus or minus 0.03. There's that margin of error. Or we estimate the proportion of people who passes out at G-forces greater than 6 to be 45% plus or minus 3 percentage points. And we estimate this with 98% confidence. Now suppose we want to conduct a study to estimate a population proportion with a certain confidence level, and we want to keep our margin of error small enough. We want a small enough margin of error that our results are meaningful. It's not very meaningful to estimate a population proportion and then have a margin of error of 30% or whatever. So in order to do that, we need to have a sample size that is big enough to give us our desired level of confidence and our desired margin of error, but not so big, no bigger than it has to be, because it's expensive. The more subjects we engage in our study, the more it's going to cost. So we have a formula to calculate our sample size, just like we did for calculating a mean with a certain margin of error. So here's the formula we have: z sub alpha over 2 squared times the probability of success times the probability of failure, all divided by the margin of error squared. So n is the sample size we're trying to find. Alpha over 2 is again the area in the left tail for our confidence interval. So for our confidence interval, if we have a 95% confidence interval, 95% of the area is in our confidence interval, and 5% of the area is in the two tails. Divide that 5% by 2 to get the amount of area in one tail. So alpha over 2, 1 minus our confidence level, so 1 minus 0.95 is 0.05, divided by 2 to get the amount of area in the left tail, or the right tail, either tail, but left tail is easiest to think of it that way. Z sub alpha over 2 is the z-score for the left-sided tail in the normal distribution for our confidence interval. And the way we calculate that is using the inverse normal function in our calculator. So we find the z-score for that left-handed area, alpha over 2. We are using a standard normal distribution to approximate our binomial distribution. So the mean is 0 and the standard deviation is 1. P is the probability of success, typically given in the problem. And it's typically given in the problem in the sense of in a previous study, we had a proportion of successes that was P equals blah, blah, blah. That will be given to you typically. And then Q is the probability of failure. And that we calculate. We just do Q equals 1 minus the P that's given in the problem. Now, if we are not given a P, if we don't have any previous study, then we would use P and Q both equal to 0.5. These are the worst case scenarios, and that would give us the largest possible sample size we could possibly need. So it's cheaper if we know something, because then we can use a slightly smaller sample size. But if we don't already have some information, go with the worst case scenario, P equals Q equals 0.5. E is the margin of error, again, typically given in the problem, with a margin of error of blah. And if it's given as a percent, turn it into a decimal. Must have decimals. All right, so here again we are doing our NASA experiment. NASA is conducting an experiment to find out the fraction of people who black out at g-forces greater than 6. In an earlier study, the population proportion was estimated to be 0.43. So that earlier study is kind of nice. It means that we have a P and can find a Q and don't have to just toss in 0.5. So how large of a sample would be required in order to estimate the fraction of people who black out at 6 or more Gs at the 99% confidence level with an error of at most 0.03? Round your answer up to the nearest integer. So again, if we didn't know already in advance, estimating the fraction of people tells us this is a proportion. We are trying to find the sample size. We know it's a binomial experiment. Success is blacking out at g-forces greater than 6. Failure is not blacking out at g-forces greater than 6. And we're going to use this information to find our sample size for a population proportion. So, values we're going to need to find the sample size. We need the P. P is the population proportion that was estimated from a previous study, 0.43. Q is the population proportion of failure, 1 minus the P from the previous study. 1 minus 0.43 is 0.57. Margin of error given in the problem, 0.03. Confidence level given in the problem, a 99% confidence interval. Turn that into a confidence level of 0.09. And we're going to go ahead and calculate our alpha over 2, the amount of area in the tails. So 1 minus 0.99, the area left outside of our confidence interval, divided by 2 to find out how much area is in each tail. 1 minus 0.99 all over 2 is 0.005. We're going to do a few steps to put these values in our TI and find the needed sample size. So remember, we've got our formula here. And remember, in order to find our z, alpha over 2, we need the inverse normal function in our calculator. So we go to second vars, which takes us to our distributions. We want the inverse normal distribution, and I'm going to go through one of the ways to do this on your calculator in the next slide. But for now, know that you get to that. You're going to enter your area, your alpha over 2, mean of 0, standard deviation of 1, and bam, out pops negative 2.575, blah, 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 blah. Don't bother writing that down. Just keep that in your calculator. Don't hit enter after that. Don't leave that in your calculator and then hit the x squared button. What that's going to do is it's going to square the result that you got. It's going to give you that z alpha over 2, which you just found, and square it. And then go ahead and leave that in your TI, times 0.43, that's your p-value, times 0.57, that's your q-value, divided by 0.03 squared. And then you're going to get a result of 1806 point blah, 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 and we don't care because you always round up on sample size. So 108 point blah, blah, blah or I'm sorry, 1806 point blah, blah, blah becomes 1807. And that is the sample size we need to get our desired confidence level, 99% confidence level, with a margin of error of no greater than 3%. And here's the TI to do
Alrighty,
it.
let's go ahead and walk through the graphing calculator, our TI calculator steps to find the sample size for the problem we've been working on. So we're using that crazy formula, and the first thing we need to find is our z sub alpha over 2. So we already figured out that alpha over 2 is 0.05. So we go ahead and we use our second VARS button because we need to use a distribution to find this z-score. Scroll down to our inverse normal and hit enter. So now here for our area, we go ahead and we enter 0.005. This was our alpha over 2. This was the area in the left-hand tail of our normal distribution if we have a 99% confidence interval. 99% of the area is in the big hump, 1% split between the two tails, 0.5% in each tail, and 0.5% as a decimal is that 0.05. Okay, so 0, 0, 1. Yes, this is a left-hand tail. Many of the calculators don't have this, so you would just do the 0.00501 and then paste or calculate or enter. All right, so go ahead and hit enter or calculate. This is the result you should get. Now leave that there. Don't clear it out. Don't write down and plan to input later. Leave that in your calculator. We are going to use our formula, and our formula asks for this z alpha over 2, this number we just found, squared. So just go to the x squared button, and that will square the result you just got. So we want to take that, we want to multiply it by our p-value, which in this case is 0.43. We want to multiply it by our Q value, which as we already found is 0.57. And we want to take that result and divide it by our margin of error squared. And our margin of error for this problem was 0.03. And again, go ahead and square that. When we hit enter, bam, out pops our sample size. Now we always round up. So we have 1806. It doesn't matter what comes after the decimal point. This will always round up to 1807. It will always round up. If you don't have a big enough sample size, if you round down, you won't meet your margin of error, or you won't have your right confidence interval. So, all right, as always, if you have questions, let me know.